Arpita is a postdoc in Pisa, and she's interested in massive star evolution. And today she will talk about the mechanisms for the origin of WNL stars, the implications on the ionization and chemical evolution of galaxies. So thank you very much, Arpita.
Yeah, thanks, Aaron. This work is mostly I have started doing my first postdoc at Australian National University. And right now I am continuing this work to include the mechanisms of massive stars and their implications into the galaxy evolution models at Scola Normale in Pisa. Or in the cosmological model. So before I go into the details of this, let me just tell you what is WNL stars. Normally when the massive stars, they move through their evolution. During the main sequence, or towards the end of the main sequence, we see the surfaces enriched with helium and nitrogen. And depending on what elements you are seeing on these surfaces, these Wolf-Rayet stars, or they have huge mass loss, and these Wolf-Rayet stars can be classified into different categories like WN, WC, WO. And this WNL is the lead type WN stars, which gets turned on already when it is on the main sequence or towards the end of main sequence, not when the core is helium burning. And then slowly it gets evolved into WNE phase, that is the early WN phase, early type WN phase, and then WC or WO, and then to the pre-supernova phase, and they go through this core collapse supernova evolution. So now, while looking at the massive stars, the question is like, why do we really need to study massive stars? So even though they are less in number compared to their low mass cousins, these are the primary sources of ionizing photons, chemical yields, mechanical luminosity. And if we really want to understand all these quantities in detail or more accurately, then we'll have to understand the stellar structure and evolution of massive stars. But the question is like, why do really cosmologists need to care, or why do they, these days they are caring for the evolution of massive stars? The reason is that if you look into at least the theoretical perspective of cosmology, so the cosmological simulations, their subset is like galaxy formation and evolution simulation. And in this galaxy formation and evolution simulation, we feed the data, which is IMF average quantities of these stellar outputs of the stellar parameters like the velocity, mass loss rates, ionizing photons, yields, mechanical luminosities, IMF average quantities of these parameters into the galaxy formation and evolution simulation. And for doing this IMF averaging or to use these stellar tracks into a population synthesis code, which actually gives this IMF average quantity which you feed into the stellar formation and evolution simulations. So there are several population synthesis codes, but particularly right now I am interested in SLUG, which is light up galaxies, but the widely used population synthesis code is Starburst 99, and these different population synthesis code takes different stellar tracks into account. And so if we do not understand these massive stars, then our ionizing photon budgets, chemical yields, mechanical luminosities, all of these quantities might go wrong. And if we feed the wrong data into the population synthesis code, we'll have the wrong output for the IMF average quantities, which will be fed into the galaxy formation and evolution simulation. So we'll eventually have wrong estimates for the ionization history of our universe or the chemical evolution of galaxies over cosmic time. And so right now the question is like, so we understand that cosmological simulations, at least the theoretical part, they need to care about this population synthesis code and what goes into this population synthesis code. But the question is like, why do we really need new stellar tracks? There are existing stellar tracks. So there are existing stellar tracks like Geneva and Padova models. And if I talk about the massive stars, but there are some issues with these existing stellar models, and I'll come into this. And because of those issues, also the population synthesis models are are not accurately predicting all these output quantities, IMF average quantities. So now we'll look into what are the different existing issues with the existing stellar models. So the most widely used stellar tracks for the massive stars are the Geneva stellar tracks, and here I have taken from their webpage. And first, there are three issues. First is the metallicity. Now, if you look into their metallicities, they do not go, I have particularly marked this region because they do not go below 1/10 of solar metallicity. But now, if you look into the galaxy evolution simulations, or the galaxy evolutions in general, and their chemical evolutions over cosmic time, there are, especially at high redshift, and if I say that, okay, high redshift is kind of, at least different metallicities can be proxies for different redshifts, then we need metallicities which are much lower than 1/10 of solar metallicity. So we need stellar tracks which will have stellar tracks which have the metallicities much lower than the 1/10 of solar metallicity. So that's one issue that we have with the existing stellar evolution models. Now, the second issue is the mass resolution. So now here on the left-hand panel, I'm showing you the stellar tracks or the HR diagram from the Geneva group, that is the main and Mayday paper in 2000. And you can see that they have plotted massive stars at solar metallicity for rotating and non-rotating cases. And when I talk about the most massive stars, not the very massive stars which have different definitions, that those are the stars that have masses more than 150 solar mass and above. But right now, when I say the most massive stars, I am in the mass range of 40 solar mass and above, so 40 to 150 solar mass. Now, if you look into this most massive star regime, you can see that they have only one massive stars in between 40 to 120 solar mass, that is 60 solar mass. And now, if you look into their, after 10 years of work, this is at 1/10 of solar metallicity, and now they have different rotation rates, but in the high mass regime, again, from 40 to 120 solar mass, they have one additional extra mass, which is 85 solar mass. So why this high mass resolution is important is because if all the stars with masses from 40 to 120 solar masses, they would have behaved in a similar pattern, then if you do the linear interpolation to create the isochrones, then you will get the accurate results. But most often than not, we don't find these stars to behave in a similar pattern. So in those cases, if they don't behave in a similar pattern, if you do the linear interpolation to create the isochrones, you will end up with having wrong luminosity and also the wrong effective temperature. And the same way, you will also have the wrong surface gravity. And if these quantities are not right, they actually determine the mass loss rates, the surface abundances, and also those things in return, they determine the ionization photon budgets in different bands. When I say different bands, I don't mean different wave bands, but what I mean is whether they're soft ionizing photons or the hard ionizing photons, hydrogen, helium, helium-1, helium-2, and oxygen-3, or harder ionizing photons. So now to have these quantities right, so you understand that we need more finer mass resolution, and I'll stress on this point later on when I'll talk about the more recent stellar tracks and how they look like. But now, if I move into the second point, which is the rotation rate. Now, if you look into this population synthesis code, the widely used population synthesis code is Starburst 99. And here again, I have taken from the Starburst 99 web page, and their latest version is version 7. And here they clearly writing that the version 7 uses this Geneva evolution track, which is the 2012 track that I have shown right now. And they also use the Potsdam Wolf-Rayet star atmosphere. And now what this Littler et al., this Starburst 99 version 7 paper they are talking about, they're saying that they are considering only two rotation rate cases, which is like non-rotating and rotating with 40% breakup velocity. And they're saying that these values are expected to bracket realistic rotation velocity distribution in stellar populations. But is that the case? Now let's look into some of the more recent stellar tracks and the HR diagram. So here I'm showing you the meso-isochronous stellar tracks, that is MIST-1. And here they haven't shown all the masses from 40 to 150 solar mass just to avoid the clutter. but they are showing for two different rotation rates of non-rotating and the 40% breakup velocity. Now, if you look at this high mass regimes, 70 solar mass, 100 and 150 solar mass, you can see that with rotation and without rotation, they go completely into the two different directions in the on the diagram. So if that's the case, and now if you say that, okay, I am taking only the non-rotating and the 40% rotation rate, and I'm saying that, okay, these values only bracket all the realistic cases, so I'm going to interpolate between them. Then you can see that they are behaving so much differently that if you do the linear interpolation, again, you will end up with the wrong values of luminosity, effective temperature, surface gravity, and eventually the chemical yields and surface abundances of different chemical elements and the ionizing photon budgets. So now to understand, okay, so right now I have talked about the three cases. One was metallicity and the issues with mass resolution, and the other issue is the velocity resolution. Now, to model them more accurately, what we are using is that MESA code, but the more modified MESA code, that is MIST1. But even in MIST1, we are modifying, we call it as MIST2 because we include the more realistic elemental abundances into account, especially the alpha enhancement into account. Because if you look at the low metallicity cases, then we see that the second generation of stars, so the supernova explosions, they actually enriches the ISM with alpha elements. And in that case, when there is the second generation of star formation, those stars have initial metallicities which are already alpha enhanced. So that needs to be taken into account if we really need to model more realistic stellar structure or evolution models. And why do we use MESA? Because MESA has several benefits in it itself, because it is open code, unlike many of the stellar evolution codes, and it has the modularity. It has 5 physics modules, and as they are standalone modules, so you can anytime change or kind of run them separately and then export them into the common library, and from there, like all the other modules can access the data from the common library. And there's this wide applicability, and also the interesting, I like the two major benefits of MESA, that is modularity, and the other one is it's at least parallelized. And although it's not MPI parallelized, it's OpenMP, but still it's better than other existing stellar codes. Now the question is like, where do we find this kind of young massive star clusters? And normally in our galactic center, we have this Arches cluster and quintuple cluster, where we have multiple of these stars, which are very massive. And during the main sequence, they show this kind of surface helium and nitrogen enrichment, which can be called as WNL stars. But when they were first observed by Figure et al. In 2002, they didn't understand why these stars, although they are on the main sequence, they are showing these typical features of Wolf-Rayet features, which is like high surface abundances of helium and nitrogen. So they call these stars as hydrogen burning Wolf-Rayet stars on the main sequence, which later on got renamed as WNL stars. And there are plenty of them in 30 DOR region of LMC, and also there are a handful in NGC 3603 and many other clusters in the nearby galaxies. But to understand this structure and evolution of these massive stars, as I said, that we use these MIST2 tracks, and MIST2 models, and here for the first part of the talk, when I'll talk about just the ionization evolution of galaxies from via the ionization evolution of massive stars, there we have mass grid, which is 62, because we are only interested in very massive range of the very massive range of the mass grid, and which is 60 to 150 solar mass with a mass resolution of 10 solar mass, and we'll have a rotation rate of 0 to non-rotating to 60% of the breakup velocity, and with a resolution of 0.1 or the 10% of the breakup velocity. And here we'll have the metallicity of solar, 1/10 of solar, and 1/100th of the solar, and we have taken into account the alpha enhancement properly at lower metallicities, which is at Fe over H less than or equal to -1. So now here I'm showing you the results for some of the alpha, some of the helium and nitrogen enhancement in these massive stars. As you can see that here I'm showing just the surface helium mass fraction as a function of velocity and time, rotation rate and time. And if we go from top to bottom, the top one is at 80 solar mass and the mass increases, so 100 and 150 solar mass. And if you go from left to right, our metallicity decreases. This is solar, 1/10 of solar, and then 1/100 of the solar metallicity. Now you can see in all of these cases, beyond a certain rotation rate, we see the surface helium mass fraction of the order of 40 to 90%. So normally for the WNL stars, if you look into the literatures from the spectra and also from theories, how they connect the spectra with the theories is that they try to observe, they try to predict the surface abundances of different elements, and then from there they try to predict, okay, if this is the surface elements of certain elements, then how much, how the spectra will look like. If you can match the spectra, that's how they connect the spectral features with the surface abundances and with the theoretical models. And so now you can see that beyond a certain rotation rates, all of these massive stars at different metallicities, they have the surface helium mass fraction, which is 40 to 90%. That is the definition for WNL stars, that there you'll have to have the surface helium mass fraction of almost 40 to 90%. And if it is beyond 90%, then it's WNE stars. So along with the helium, you can, I'll now show you the nitrogen. And you can see that here, the nitrogen, I'm not showing just the mass fraction of nitrogen. Instead, what I'm showing the mass fraction of nitrogen compared to its initial nitrogen abundance. And you can see that this nitrogen, surface nitrogen enrichment happens, which is pretty huge. And it's depending on the metallicities, it can be almost 13 to 17 times to almost 30 to 33 times higher compared to its initial abundances. So these are definitely, and they are all in the main sequence because we have normalized time with the main sequence lifetime. And you can see that these are kind of classic, they fit the classical definition of the WNL stars. Now the question is like, okay, the question is, how do we dredge up the elements that are being produced within the very central core of the stars via nucleosynthesis, and how do we dredge up these elements from the core to the surface? Now, massive stars, if you look at their structure in the schematic diagram, you can see that they have a huge convective core, and they have a radiative zone in between the huge convective core and a very thin outer convective layer. So all the elements that are being produced within this small core, these nucleosynthetic byproducts, they are getting almost chemically homogeneously mixed within this convective zone. But then there is this river of radiative zone. So you'll have to somehow cross this river to reach to the outer convective layer, where again, they will be convectively mixed. So now when the star is rotating, as we know that the star gets flattened, and because they get flattened, we have the thermal imbalance between pole and the equator. And because of that, as many times mentioned during this call, that we have this large scale circulation, which is known as meridional circulation or Eddington-Schwitt circulation. Along with that, as the star, because the stars are differentially rotating, so when two different layers of different rotational velocities come in contact with each other, there are small eddies turns on because of the shear instability, and these small eddies can also help in mixing the chemical elements. And if along with the rotation, if we have the magnetic field turned on, then also there can be the mixing due to the spiritual dynamo mechanism. So on the right-hand side, I'm showing you the diffusion coefficient as a function of mass at different radii for a 100 solar mass star. I'm showing it at a time of 2 million years when the star has lost its mass, and right now current mass is of the order of 80 solar mass. You can see that we have this huge inner convective core, and we have very thin outer convective layer, and in between this radiative zone, the materials get dredged up by different rotational instabilities and mixing due to different rotational instabilities. But now, if you look into, but the question is like, okay, if you have the rotation, you can somehow transport you can transport the element from the core to the surface. But the issue came up when there had been observations of WNL-like surface abundances in slow rotators or non-rotating stars. So in 2000, Herrero et al., they found almost 3 WNL kind of stars which had rotational velocities which are almost like very slow rotators. But the question is like, okay, you can say this is very old observations. Probably there were some issues, but recently there is this Fink et al. Observations of 2017. They have observed 4 stars, 4 WNL kind of stars in among the 39 Wilfred stars in LMC, and they also found this kind of surface enhancement, and they are slow rotators. So they hypothesized, saying that probably this kind of observation actually challenges the existing rotationally induced chemical homogeneous evolution models. Probably there is a different dredge-up mechanism. Now, as soon as the Herrero et al.'s paper in 2000 came out, the Mene and Mader 2000 paper, they they gave some hypotheses that how you can have this surface enrichment in slow rotators. So what their hypothesis is that what they're saying that, okay, these slow rotators, what you're seeing today, they actually started their life as fast rotators. And when they were fast rotators, they had this chemical homogeneous mixing of chemical elements. But then as the star lost its mass, and due to the mass loss, they also lost its angular momentum, and they slowed down. So today they are slow rotators, but when the mixing or the surface enrichment that you are seeing, that had happened when they were first rotators earlier in their life. That is a feasible explanation, but if that's the only possible way to enrich surfaces of slow rotators, then we shouldn't see anything for the non-rotating stars. But in our models, we could see that if stars are massive and metal rich, we can see even for the non-rotating stars, the surface enrichment, which is almost 40% to around 70 to 80%. So how can we have then this kind of surface enrichment for non-rotating stars? That's the question. And the same happens for the nitrogen as well. So now here I'm going to talk about a different theory which we have proposed in this paper, and which is the exposure of fossil convective source. Okay, before I go into the detail of show you the movie, before I go into that, let me tell you what is happening physically. So what is happening is that these stars, because mass loss is dependent on 3 parameters. One is the mass of the star, one is the velocity, and another one is the metallicity. So if you keep the velocity or the rotation rate constant on non-rotating stars, so what is happening is as your star is more massive and metal rich, you have the more and more mass loss. And if you have the more mass loss, as the star loses its mass, it's also shrinking. As it's shrinking, is showing up more and more of its inner cores. And that's how they are exposing those inner regions which have already been enriched with these heavy metals. So we call these as fossil convective core, because these are not the convective cores of the present time, but the convective cores of the past time, which had already been enriched with these nucleosynthetic byproducts. So now here, before I go into playing the movie, here on the left-hand side, what I'm going to show is that the diffusion coefficients of all these non-rotating mixing mechanisms, that is convection and the overshoot, the major non-rotating mixing mechanisms for these massive stars, and as a function of stellar radii, or you can say mass at different radii for a 100 solar mass star. And on the right, like on the right y-axis, we are showing the helium mass fraction. So helium mass fraction is shown by this black, and the diffusion coefficient is shown by this red. And I'm starting at a time which is very early in its evolution, which is around 0.2 million year, where if you look into this core region, or the inner convective zone region, there the helium mass fraction has been increased into 30%. But if you look at this surface, it is not yet enhanced with 30% helium mass fraction. So the question is, when can we have this helium mass fraction on the surface, which is 30%? On the right-hand side, I'm going to show the schematic diagram of the star. And here I have color-coded it according to its helium mass fractions. As you can see, that inner convective zone has higher mass fraction, and as it goes to outer radiative layers and the thin convective zone, the mass fraction, helium mass fraction, decreases. Now, as I move in time, I'll just go to the next time step to show that as I move in time, every time the present time value would be shown by the dark colors, and the past time's values would be kept by the faded colors. And here on the right-hand side for the schematic diagram, I'll just keep the outer layer of the inner convective zone by this dashed pink line. Now I'll play the movie and let's see when on the surface we have this helium mass fraction of 30%. See, now the star is losing its mass. As it's losing, it's shrinking. That the surface is not yet enhanced with 30%, but as soon as the surface convective zone falls on top of the fossil inner convective zone, the surface enhancement happens and the surface helium mass fraction reaches to 30% value. I'll play the movie once again. So now the star is losing its mass, it's shrinking. As it's shrinking, it's exposing more and more of its inner layers. And as soon as the surface convective layer falls on top of the fossil convective core, we see the surface enrichment happening. Now, let's take another case, which is at a different time, and at, when I'm starting at a time when it's almost 0.7 million year, when the inner core, in the inner convective zone, the surface helium, the helium mass fraction is 40%, but surface is not yet enriched with 40%. So the question is, at what time the surface will be enriched with 40%? The same goes. Now the star is losing more and more mass. It's shrinking. And as soon as these two regimes fall on top of each other, you will see the surface enrichment to exactly the 40% of helium mass fraction. So now this theory is actually why it's very natural mechanism or phenomenon for metal-rich massive stars. And for them, you really don't need to invoke any kind of havoc stellar spin down kind of scenario. So this is a more natural way to enrich surfaces of massive stars with heavy elements if they're metal-rich and massive. But whatever be the mechanisms for surface enrichment for rotating and non-rotating stars, the question is, can we really produce the spectra? Now here, what we do is like we feed our stellar track output into the stellar atmosphere code CMF-GEN. And this is this particular star of 100 solar mass we have modeled with LMC metallicities. And here we, on the left-hand panel, what we are showing is the normalized flux as a function of wavelength in the range of 4,000 to 4,900 angstrom. And these red ones, this black one is our model spectra, and these red solid lines are the observed spectra by VLT Flame's Tarantula survey for 3 different stars. And now you can see that our model spectra matches pretty well with the observed spectra with these specific features of these kind of WNL stars or the O2 stars, which has these specific N4 lines, N4 emission lines, and almost absent or very weak N3 lines. And also we have these huge helium-2 emission along with some helium-2 and hydrogen absorption, very thin absorption lines. And now on the right-hand panel, what I'm showing is the same normalized flux for an extended wavelength range, so almost 3,500 angstrom to 8,000 angstrom. And here, the bottom, the solid line is our model spectra with CMF-GEN, where we have taken into account the surface mass fraction more accurately, because surface enrichment of helium and nitrogen is happening, because we know that during the main sequence surface enrichment happens. So I've taken that into account accurately. But the issue with most of the stellar atmosphere modeling is that they do not take into account this surface enrichment. They assume that during the main sequence, the stars have almost an unevolved surface abundances, and therefore they keep the abundances same as with what they had started with. And if we keep the unevolved surface abundances, then we can, again, we have tried to produce with the CMF-GEN the spectra, and that looks like this top one, this dotted one. And you can see that these look very, very different. And most of the time, the stellar atmosphere people, as they don't take into account this abundance properly, they sometimes conclude that probably there are issues with either atmosphere modeling or probably the observation. But if you take into account this abundance correctly, surface abundance correctly, then you see that we reproduce the spectra, which is what is the observed spectra. Now, more than reproducing the spectra, the major issue comes up when people, what they do is like, depending on how you produce the spectra, you have different ionizing photon budgets in different ranges, like hydrogen ionizing age, helium-1, helium-2, oxygen-3. Although we have seen that if we try to look into the hydrogen ionizing photon budgets or the Lyman continuum photon budgets, then these two cases show almost the similar results. But the major issue comes at the hard ionizing photon budgets. So in the helium-2 and oxygen-3 ionizing ages, we have seen that these evolved spectra shows almost 20 times less ionizing photons compared to the unevolved spectra. So if this is not estimated correctly, most of the optical astronomers, they try to estimate their metallicities of different nebular metallicities based on what ionizing photon budgets or estimates we are getting at these different ionization ages. And if they are wrongly estimated, then probably all these optical astronomers, their tools need to be updated with these kind of evolved spectra and the ionization budgets from that. So now the question is, like, after we understand more or less about how the ionization photons are getting produced in these massive stars and how they can be modeled more realistically from the stellar atmosphere modeling and fitting the right data from the stellar tracks. Now the question is, like, can we really look into the chemical evolution of galaxies from these massive stars? So this is the second part of my talk. And here I am mostly going to concentrate on the nitrogen abundance. Why nitrogen is important? Because if you look into the high redshift galaxies, then most of the metallicity estimate, they are dependent on the N/A ratio. So when now I'm talking about the metallicity, I am not meaning F/H, but I'm meaning the nebular metallicity, not the stellar metallicity, but the nebular metallicity O/H. So we have done this transfer from F/H to O/H accurately, very carefully. And the issue that why nitrogen is important is also that at high redshift, normally all these estimates of metallicities or O/H, they are dependent on N2, H alpha, O2, and S2 doublets. But at high redshift, mostly these O2 doublets are often unobservable, and so we are left out with N2 by H alpha and N2 by O3. And sometimes even O3 O3 line is not absorbed, so we are left out with H alpha, N2, and S2 doublets. So somehow we'll have to have an estimate based on this N2 by H alpha and N2 by S2 or some combination of them to have the estimate for the metallicity or the O/H. So in all these cases, you can see that nitrogen is very common. So if we really don't understand how the nitrogen is being produced, especially because given the nucleosynthetic origin of nitrogen, which is very complicated, it can either have the primary origin, it can also have the secondary origin. But which origin is taking place and for what kind of massive star ranges, that gives a completely different estimate for the nitrogen yields. And so we need to really study the nucleosynthetic origin of nitrogen, and what are the different measurement methods that had been used to measure this nitrogen and oxygen measurements. Normally for the Milky Way, we see these halo stars, which are metal poor stars, and they can be they can be used as kind of archaeological records of metal poor environments. And also there are H2 regions in the Milky Way and also the nearby galaxies, and these different H2 regions at different overall metallicities. And you can say that different metallicities are kind of proxies for galaxies at different redshifts. And there is the third method that one can have to observe nitrogen and oxygen, and that is the hoping to observe these high redshift galaxies directly, which is kind of almost not yet done properly, and this is pretty challenging. So right now, all the tools, they are dependent on metal poor halo stars and the H2 regions at different metallicities and dwarf galaxies at different metallicities. So here I'm going to show you this N/O, this log N/O as a function of O/H, and for different observed data from stars and for halo stars, H2 regions in local dwarfs and DLAs. And here we have categorized them in two classes, stars and gas. So stars are whichever has been observed from stars, and gas is whatever we observe from H2 regions, dwarfs, and DLAs. And now if you look into how the N by O is distributed over O by H, you can clearly see that there are two regimes. One is the low metallicity regime, which is at 12 plus log O by H value of almost less than 7.5. And you can see here that nitrogen by oxygen is almost constant with O by H. So now we know that oxygen has the primary origin. So if nitrogen has the primary origin, then this constancy can be explained. But along with this plateau, we can also see the scatter of N by O, which is almost of the order of 1 dec. So the question is, does nitrogen have a really primary origin at this low metallicities, or does it also have the contribution from the secondary origin? Although if you look at the high metallicity regime, there the origin of nucleosynthetic origin of nitrogen is quite well understood. They have the secondary origin coming from the intermediate mass stars or the AGB stars. And so in today's talk, I'm not going to stress on how we can explain this high metallicity regime, but more talking about how we can explain this plateau and scatter at the low metallicity regime. So before I go into the details of showing our models, how well our models fit with these observations, here I'll just talk about our grids of massive stars. And we have here the grids from like it's more massive mass ranges, like more massive grid of mass ranges, which is like 10 to 150 solar mass with a mass resolution of 5 solar mass. And we have the rotation rate of 0.2 to 0.6 with a resolution of 0.2. And the metallicity, because we are looking into the lower metallicity regime, we go from 1/100th of solar metallicity to 1 by 10 to the power 5 times the solar metallicity. Or Fe over H, if I talk about the logarithmic scale, -2 to -5. And we have taken into account the alpha enhancement. So now, before I show you the models, let's just talk about how we estimate these different abundance ratios, like this N by O or O by H that we are talking about. So now our yields that come from both wind and supernovae. And here, if you think like I have a stellar population of average mass, say M, and now any element X that is returned to after the star formation, those gas has converted into stars, and after the star formation had happened, these stars, via their feedback through wind and supernovae, they enriches the ISM. So any element X that is returned to the gas phase at any time t is per unit mass of the stellar population is defined by this. And this first part comes from the wind contribution and the second part from the supernovae contribution. Now, if we assume that we have a gas reservoir of mass mg, and epsilon star of this mg is getting converted into stars, and if we have this F0x, which is the mass fraction of an element X, which was pre-existing in the ISM, then this is the total mass of an element X at any time t. So as we know the mass of these different elements at any time t, we can have their ratios to have the ratio of mass fractions, and we can convert them into the number fractions via taking into account the atomic weight. So this nx by ny we are going to call as x by y, or O by, depending on what element we are using, it will be O by H or N by O. So now, if we look into this low metallicity regime, I'm just going to show how our model turns up. Now, on the top panel, for the timing, just look at the top panel, and where we haven't taken into account any yields from supernovae. It is just the wind yields, for different metallicities and for different star formation efficiencies. And as you can see that our models not only explains the plateau of N by O at these low metallicities, which is of the order of log N by O of -1.8, but also it explains the scatters, that the scatter arises from different metallicities and the different star formation efficiencies. Now you can see these horizontal lines, you can think like probably they're error bars. They're not the error bars. What we have assumed in our models is that after the star formation event had happened, these galaxies or these systems, they are actually accreting they are accreting primordial gas, which is pristine gas. They are hydrogen and helium. So depending on what our assumption of how much of this pristine gas has been accreted, we show these ranges along the x-axis. But as you know that these galaxies or these systems, they can accrete more and more primordial gas. So sliding this value down to lower values of O by H is not an issue. So we can easily match these x-axis, observed x-axis values. But the issue is if we can explain these y-axis values. So this is N by O. So as you can see that this value can easily come down over here, and all our models actually can explain not only just the plateau, but the scatter, when we do not include the supernova yields. But as soon as we include the supernova yields, in the bottom panel, you can see that the supernova yields give higher amount of nitrogen and oxygen. And because of that, we see that N by O is almost an order of magnitude higher, or 1 dec higher from what has been absorbed, or what we can produce via the wind yields. Now, this result is very important from the perspective of galaxy evolution. Why? Is because that if you look at these low mass galaxies like the dwarf galaxies, then they have low galactic potential. And because of that, they would easily be able to retain this low velocity wind ejecta, but probably this high velocity supernova ejecta, they might escape these galaxies. So so probably these supernova yields might not be able to enrich these dwarf galaxies. And if we can explain this metal enrichment coming from the wind yields, then we can explain the mass metallicity relation in dwarf galaxies. So this result has huge importance in understanding the metal enrichment of dwarf galaxies over cosmic time. Now, I am not going into the details here in this talk, but we have looked into the nucleosynthetic origin of this nitrogen, and we figured out that mostly if a system is very young, which is like almost 3 million years or so, or less than that, then we have the purely secondary nitrogen. But at a later time, if they are old enough in the sense like 5 million years or above, they have both primary and secondary contribution, but primary is being dominated over secondary. And as the metallicity decreases, primary domination actually increases. And so we have shown this primary to secondary ratio as a function of metallicity at lower metallicities, and their metallicity, and we have discussed this metallicity evolution of these primary to secondary nitrogen ratios. So that way, I'm not showing here. I'm not going to talk about that in detail here. And also we have shown that how different elements, not just the supernova velocities or the wind velocities are different, but also how different elements like nitrogen, oxygen, all of them come out with different velocity beings and different velocity ranges. And if we'll be able to contain these low velocity materials, or retain these low velocity materials, and explain this N by O plateau and the scatter. And we could explain that pretty well. So for that, please look into our paper. Right, of 2021. Now here, right now, currently what I'm working on is that now we have different stellar tracks like MESA, MIST-1, MIST-2. MIST-1 has these solar scale abundances, and MIST we have this alpha element enhanced abundances. But we also have these Tromlo stellar tracks. Why? Because if you look into this galactic concordance abundance setup, then not that all the alpha elements are enhanced equally, where we see that oxygen is enhanced more than other alpha elements, and where calcium is enhanced less. So we will have to take into account all these alpha elements separately, like their enhancements separately. And to incorporate this galactic concordance abundance setup, or more accurate elemental abundances into stellar tracks, we have modeled the massive stars, the tracks of massive stars, which we call as Tromlo stellar tracks, because it has been done in Australian National University, and that and our astronomy astrophysics department is situated in Mount Stromlo, and that's why I call it as Stromlo stellar tracks. So right now what I'm working on is that we have these different stellar tracks at different metallicities as low as Fe/H of -5 in the log scale. So now putting that back into the population synthesis code, that is SLUG, I'm using this stochastically lighting up galaxies because it has the stochasticity and which has very important role when we have this low star formation rate in dwarf galaxies. And then feeding that IMF average quantities back into the galaxy evolution simulations. I also did during my PhD, I did the galaxy evolution simulations and studying the stellar feedback, mostly the supernova feedback, and producing this huge super bubbles or the huge shocks where multiple supernova explosions are coherent in space and time, and how they evolve and how can we implement them numerically more realistically, and what are the different implications they have on the escape of ionizing photons or the in situ molecule formation for the starburst nuclei, etc. And also during my first postdoc at Australian National University, I worked on the superbubble momentum, estimating the superbubble momentum budget using different codes like Gizmo, Ramses, and ZeusMP. So they are particle and the grid codes. So right now, what we're trying to do is like kind of bridging the gap between the galaxy evolution models and the stellar evolution models, especially the massive stars. So putting these tracks back into the population synthesis code and then the output back into the galaxy evolution simulations to study different properties of galaxy evolution more realistically, like to study the metal enrichment of dwarf galaxies over cosmic time, or to study the mass metallicity relation of dwarf galaxies, or like the ionization evolution of galaxies up to the time of reionization of early universe. And also if these kind of different stellar feedback, wind feedback can produce the stellar wind-driven bubble, which had been observed in X-rays, both in Milky Way and LMC. And also there are different nebular emission lines if we can model them or produce them. So right now I'll probably conclude my talk and with the major points that massive stars, they evolve into these WNL stars with considerable helium and nitrogen abundances if they are rotating, and also if they are non-rotating, then we have different mechanism which we call as the exposure of fossil convective core, and that can also enrich the surfaces of massive stars with heavy elements if they are massive enough and if they are metal rich. And also we have produced the spectra from feeding our stellar tracks back into the atmosphere code, CMF-GEN, and we could reproduce the spectra pretty well that match with observations. And we could see that if we have evolved spectra, and then we'll have the ionizing photons at the harder bands like helium-2 and oxygen-3, which are 20 times lower than if we have the unevolved spectra. And now coming to the chemical evolution, I could say that our wind models can not only explain the plateau of N by O, which is at low metallicity, which is at log N by O of -1.8 or 2. And also our models can explain the scatter in them. And supernovae models produce, so supernova yields actually produce N by O, which is an order of magnitude higher. So probably at the high metallicity regime for more massive or metal-rich galaxies, probably supernovae ejecta, they have higher galactic potential, so they probably will be able to retain the high velocity supernova ejecta and their yields. So these galaxies can be enriched with supernova yields, along with other secondary nitrogen production coming from intermediate massive stars and AGBs. So yeah, this is all about chemical evolution and the ionization evolution. Thanks for your patience.